So let us start today with the solution of the numerical. In the statement we have been given this is a vehicle for launching the rockets and all in case of the army. So this is your gun barrel and this is the vehicle who is keeping all this kind of arrangement onto it. This is the gun barrel and gun barrel is loaded on a truck. And the truck is further carrying a damper and a spring system so that the complete vibrations can be controlled and absorbed. Point number 1. Point number 2, the gun barrel fires this projectile and due to the firing the velocity of the projectile since it is very high, so this barrel goes in the backward direction and comes to the initial position. So, in that condition, we have been given the stiffness of this spring as 300 Newton per mm. That can also be written as 300 into 10 raised to power 3 Newton per meter. Point number 1. Point number 2, the mass of the barrel is given as 500 kg. And point number 3, the recoil comes out to be 1 meter, means this complete barrel goes backward through a displacement of 1 meter from the main position and comes back to the original position or the initial position within minimum possible time. Please mention these words, underline, that the system comes back to the original position or the initial position or the equilibrium position in a minimum possible time. Once we are given that it is returning back to the minimum time, so that means if the system returns to the minimum time, to the initial condition, that means the system is critically damped. Point number 1. So, if the system is critically damped, in case of a critically damped system, the value of your damping factor will be equal to 1. So, moreover, the mass is given, displacement is given, K is given. So, from all these things, we can first of all we'll find out the natural circular frequency, that is omega n of the system. So, omega n of the system will be equal to root of K by m. We know the values. So, value of K is over here, that is 300 into 10 raised to power 3 divided by value of M as 500. So, the complete system value of the natural circular frequency of the system comes out to be 24.4 radian per second. We'll keep it over here. Now, second point, the potential energy of the spring, since it is going downward, so the spring gets stretched. Since the spring gets stretched, so what will be the potential energy stored, and it will release that potential energy during the recoil of the gun barrel, means when it is coming back to the original position, it is responsible. So it is given as half of kx square. Put the value of k over here. Put the value of x, that is displacement. So displacement is since 1 meter, so 1 का square हो गया यहाँ से. So that comes out to be 150 into 10 raised to power 3 joules. Next point, the kinetic energy of the barrel is given as half of mv square, half into m is here 500 and v is here as it is. So we have to find out the kinetic energy of the barrel also. So 250 v square joule. So this is the velocity of the barrel and this is the kinetic energy of the spring. Both the energies should be equal so as to keep the system into the equilibrium. So we will compare both the kinetic energy as well as the potential energy. So 150 into 10 raised to power 3 is the potential energy in the spring and this is the kinetic energy of the barrel, because barrel is moving like that. So both the things must be equal. From here we can find out the velocity of the barrel, at what velocity it is coming back to the original position or the initial position. Now, second point, we have to find out the damping coefficient. That is in this case, especially in this numerical, the damping coefficient will be equal to your critical damping coefficient, CC, because your damping factor is 1, because the system is coming back to the original position within minimum possible time. So damping coefficient will be equal to Cc in this case, and Cc is equal to 2m omega, and we know the values. So 2 into m का value आपने 500 ओमेगा एन का वैल्यू आपने यहाँ से ऊपर से निकाला वो रख दिया. From here we have find out the value of damping coefficient as 24.4 into 10 raised to power 3 and units are Newton second per meter for the damping coefficient. So the last question was we had to comment in the numerical whether the system, what type of system is it, what kind of damping is it. So in the statement itself it has been given the system return back to the original position within minimum possible time. So we can comment that the system is critically damped system and in that case damping factor will be 1. Now I must go to the numerical number side. In this numerical, we have been given a system whose mass is m and the system is having 8 oscillations. Moreover, it is also given that it completes 40 cycles in 25 seconds. This is also given the frequency. From here, we can find out the damped frequency of the system. So, moreover, one more thing is there that in the numerical we have been given that the amplitude of the system in the 8th cycle becomes 1/8 of the initial amplitude. Let it be initial amplitude is your x naught and amplitude at the end of the after 8 oscillation this is your x8. So, in the numerical we have been given that the amplitude at the 8th oscillation is 1/8 of the initial amplitude. This is a given condition. We have not written it at our own. Neither it's a formula. It has been given in the numerical that x8 equal to x0 divided by 8. It decreases to 1/8 of the initial amplitude. We have it. Or from here we can also rearrange it as x0 divided by x8 divided equal to 8. Now, point number 3, we know the formula of the logarithmic decrement that we have to find out the logarithmic decrement in the statement. So, logarithmic decrement equal to 1 by n, where n is the number of oscillations, that is also given, that is a log of e, x0 is the initial amplitude and xn is the final amplitude of the nth amplitude. Since we have been given 8 oscillation means x8, x0 divided by x8. From x0 divided by x8, this is your 8. So 1 by n is your 8, log of p 8 equal to, from here the value of logarithmic decrement is here, that is 0.25, 0.2599. Now, next point we have to find out the damping factor, that is zeta. Zeta is a delta upon 4 pi square delta c. Now ask me from where this formula came. This formula came from here. We know the logarithmic decrement delta equal to 2 pi zeta upon 1 minus zeta ka whole square. If you rearrange this equation, from here we can find out, from this equation we can find out this relationship very easily. So that is why I have written this formula for your equation. From this formula we can put the value of delta, logarithmic decrement, pi ka value aapko malum hai. From by putting all these values we can calculate the value of damping factor, that is zeta equal to 0.0409. What does it show? Zeta is less than 1. It means the system is under damped. So it will take more time to come back to its original position or the initial position. Now, next point, we will find out the natural frequency FD of the system. So, natural damped frequency, basically we had to natural frequency of the damped vibration. So it has been shown as the FD, so it's a damped one. So we can find out the number of the cycles divided by the time period. From here we can find out the frequency. So the number of cycles are 40 divided by 25. This is 1.6 hertz is the damped natural frequency. If I need to know the circular damped frequency of the damped system, that is omega d divided by 2 pi equal to fd. I know the value of fd, so omega d will be equal to 2 pi into fd. So 2 pi into fd the value 1.6 है, so the value of omega d comes out to be 10.05 radian per second, means the damped circular frequency. Moreover, I know the relationship between the damped circular frequency and damped simple natural frequency. So this is the relationship. From this relationship we can find out the value of the natural circular frequency. Omega n is your natural circular frequency, and it is the damped circular frequency. So from put the value of omega t over here, omega n we have to find out 1 minus zeta का value on 1 over 0.0409. We have already calculated it from the step number 4, and from here we can obtain omega n as 10.09 radian per second. Now next point we have to calculate. Moreover, we have to calculate k. What is k? So omega n we have already calculated. We know the relationship omega n, k and m. So omega n equal to root of k by m. Put the value of omega n. We have already calculated in our last step. So 10.09 equal to k upon 20. 20 is the mass that is already given. From here we can calculate k as 2.2039.27 Newton per meter. Now last factor we have to calculate into that is your damping coefficient. Damping coefficient if you need to calculate, that is zeta equal to c upon cc, that is c equal to 2m into omega n. From put the values of zeta we have already calculated, that is 0.0409 equal to c we have to calculate. Damping coefficient we have to calculate. So c upon 2 into m is 20 we have given, and omega n we have already calculated 10.09. Put the value, and from here we can obtain the value of c as 16.5 meter second per meter. Thank you.